All righty. Hey, folks, how we doing here? Good to see you all. It's a wonderful Sunday morning here, getting ready to go with the family to church. But I thought, you know what? Let's go ahead and do a real quick video here before we head on out here. So we're going to continue going through this idea of integration a little bit, and we've been talking about this idea of Riemann sums, right? Gottfried Riemann. I'm sorry, wrong person. Actually, I forgot his first name. All right, well, that's what happens on an early morning. So, anyways, we've been working our way through Riemann sums here, and Gottfried is Leibniz. Oh man, yeah, well, it don't matter. You're like, who are all these people? It doesn't matter. All right, so we're working our way through Riemann sums, and we've looked at how we can do different types of sums. We can do left sums, right sums, midpoint sums. We even talked a little bit about something called a trapezoidal sum. It's not actually a Riemann sum, but it's still a sum that we use nonetheless. And then Riemann sums, we found that they were actually related to this idea of a definite integral. So we have a times b. A is what we call our lower limit, b is our upper limit, or some people call them bounds. Doesn't really matter. So Riemann showed that Riemann sums are tied to this idea of a definite integral. Now, what ended up happening was kind of a cool little deal. And this is where Leibniz comes in. It was about later half of the 1700s. We had two guys, Isaac Newton, or Sir Isaac Newton, and Gottfried Leibniz. Now, they noticed as they were playing around with this idea of calculus, formulating the foundations of calculus, they noticed that there was a relationship between derivatives and integrals. They were noticing that somehow there is this idea that kind of ties them together. And later on, this idea became known as one of our fundamental theorems in mathematics. Now, we only have, I believe it's 8 if I'm off the top of my head. We've only learned about one up to this point, the fundamental theorem of algebra. But what they found out became the second fundamental theorem of mathematics. It's called the Fundamental Theorem of Calculus. And here's essentially what it said. It said, let f of x be a continuous function. I should make that a little longer. There we go. And by the way, if it's called fundamental, chances are it's kind of a big deal. So we're gonna be playing with this one this entire rest of the year. Some people call it FTC. In AP Calculus, that's not an approved abbreviation, so I wouldn't worry about it. Well, you can't use it. You'd actually call it fundamental theorem of calculus, but you'll never actually write that. Anyways, let f of x be continuous on the closed interval from a to b, and let f of x be the antiderivative for f of x at a and b. And if that's the case, then, oh, come on, Ben, get up there. There you are. Then we get the fundamental theorem. And here's what it says. It says that if I were to take this integral, and if I were to integrate it, so lowercase f becomes big case f, turns out the value of that definite integral is big F of b minus big F of a. So it turns out, amazingly, we can actually take this one step further, and now we don't have to actually do a sum anymore. We can actually figure out the exact value underneath any curve by integrating. And friends, that was pretty much groundbreaking. So how does that work? Well, let's try an example. Say I give you something like this. Oh, let's go 1, 4, 3x squared minus 2x. We'll keep it real easy here. And first thing we're going to do is we're going to integrate it. Now, guys, I'm going to leave off the plus c. I know we've been hammering that in class a lot. Don't forget c, don't forget c, don't forget c. I'm going to leave it off. I will show you where it goes here in a second. Okay? Because on definite integrals, you don't need plus c. Only on indefinite integrals. Okay, so we integrate. We do our power rule. X cubed minus x squared. And then that's going to be from 1 to 4. And we're going to plug it in. So we have 4 cubed minus 4 squared. So that's f of b right there. That was my evaluating it for my upper bound. And I'm going to subtract my lower bound. 1 cubed minus 1 squared. So this is the fundamental theorem of calculus. I don't have to use sums. I don't have to do any of that stuff. If I integrate it, I can evaluate that definite integral for the bounds, and I can actually figure out the exact value under this curve. I don't need to use geometric area. Literally, I find the exact value. And guys, this is really, really powerful. This is really cool. Turns out the area underneath that curve from 1 to 4 would have been 48 units. Now, sometimes you're going to hear people not use the word area. They're going to use the word displacement. And that's because sometimes area can fall below the x-axis, and that makes it a quote-unquote negative area. So throughout the rest of the semester, we're going to use the word area and displacement. We're going to go back and forth between the two. So just realize, same thing. You hear area, you hear displacement, same thing. Now, here's what I'm saying about the plus c. Let's come back to that, because I know some of you guys are wondering, where'd they go? Just so you're aware, they didn't go anywhere. It's just they always end up canceling each other out. And because of that, it's understood that for a definite integral, you don't ever need to do plus c, only on indefinite integrals. And I just did it again, didn't I? There we go. So we're going to plus c here at the end. We're going to evaluate that from 1 to 4. All right, friends. So when we plug this in here, notice we still have our 4 cubed. We still have our 4 squared. And then there's our plus c, would just be hanging out there because only plug it in for x. Minus notice how I always have to put the f of a part in a bracket because I got to remember that negative there, I have to distribute it. And I'm not going to go through and evaluate this all the way down. We'll go one more step with it. So if I put the plus c there, we end up with 64. I guess I will probably just put the 48 after this here in a second, plus c. minus 1 plus c minus c. But notice what happens here. On our, if we were to use the plus c's, they would always end up eventually canceling each other out. So for definite integrals, we never actually use plus c. We go ahead and just drop them. So you don't ever need to use plus c on a definite integral. Only you got to use it for indefinite integrals. Okay, so we won't be using plus c from here on out. But anyways, this is the fundamental theorem of calculus. It's a pretty darn cool idea, right? You just integrate and then evaluate. It's not bad. So let's try a few of these here. Oh, let's see here. And we're going to keep it simple today. We're going to break it. We're going to add a couple little things that aren't necessarily in our book per se, or much in there. So we will be doing 4.2, or I'm sorry, 4.4 in 2 days. So we're going to integrate this one, and let's integrate this one. We'll go from 2 to 5, and we'll go root x minus 1. And we'll end with one more here. How about we make it from 1 to 2? 1 over x plus 2 squared. All right, so you guys already know how to integrate. So go ahead and pause the video here and take a chance, take a try. Integrate all 3 of these expressions, and then unpause it and we'll keep going. All right, friends, here we go. Let's see how you did here. First up, we have our integrals, x cubed over 3 minus x squared over 2 plus 1, I lied, plus 1x. So we integrate it, and we're going to integrate it from 0 to 3. So now, on the, and you guys heard me say this many times, on the free response portion of the test, we will not simplify it once we put our numbers in here. But on the multiple choice portion, we need to be able to actually go ahead and evaluate this. So we have 3 squared over 2 plus 3 minus, I'm going to plug it in there, but realize if I plug 0 in there, all these are just going to be 0. So this is kind of a little bit of a pointless thing, but we still need to do it. Still need to show that it's 0. So plus 0. And then we'll just pretend this thing's on a multiple choice. So we're going to go and evaluate it. So 3 cubed is 27, divided by 3, that's 9, minus 9 halves, plus 3. 12 minus 9 halves, that would be 15 halves. There we go. Let's try this next one. Now, before I do this one, though, I would probably turn this one into, you probably guessed it, fractional exponents. Alrighty. And now we go ahead and integrate, friends. So we end up with, and there's 2 different ways to write the notation for, by the way, this definite integral. I use the full bracket. Some people only put a brackets on the right side. Both are right. I just find it easier for myself to put it on both. So if you're ever combing around the internet, you'll find out sometimes they'll use a little slightly different notation. It's not wrong. Neither one's wrong. It's just, this is just what I use. So we all have our preferences. All right, so we're going to plug in the 5 here. Now, if this was, again, the FRQ part, I would stop right here. But multiple choice, we got to be able to do a little bit of arithmetic and get a little bit further along here. How cool is this? I mean, it doesn't matter what the curve is, we can evaluate any area. 5 minus 1 is 4. The 2 tells me square root, so that's 2. And then cubit is 8 times 2, that's 16/3. We can find the actual exact area underneath the curve. Friends, I think that is so crazy cool. We can find any value we wanted to. Now on this one, again, I would rewrite it, get that thing out of the denominator there. All we have are trig rules and the power rule. Trig rules and the power rule. Time and time again. So -2 dx. All right, we do ourselves a power rule here. So we're going to add 1 to it. And then we're going to divide by -1. And we're going to do this from 1 to 2. And just for the sake of argument, because I'm going to go ahead and evaluate this, I wouldn't do it normally, but because I am going to evaluate this, I am going to rewrite this here, make it a little easier on myself. There we go. All right, so I got -1, 2 plus 2, minus a -1 over 1 plus 2. So -1/4 plus 1/3, and that would be equal to 1/12. Again, this FTC thing, it can do all kinds of things. I think it's just ridiculously awesome. So we're finding the area under the curve, or we're finding the displacement of the value. So we keep going here. You know, turns out it works just as well with trig as well. So we have sine. Let's try this one. I'll throw a couple of these up here for you. We'll make this 0 and pi over 2. And let's do secant squared. Pi over 6. Now, here's one, just like derivatives, you have to evaluate a trig value. So when I plug in my trig into my answer, I have to simplify the trig expression. I will get docked for that, both on the FRQ and, of course, on the MCQ. All righty. Friends, why don't you go ahead and pause the video and see what you guys can do with these ones. All right, so sine. All right, I'm sure there are a couple of us out there that put cosine, but remember it's negative cosine, negative cosine. So we got to know our actual trig rules. And we're going to plug everything in here. So we end up with negative cosine of pi over 2. It's so easy to get the derivative and the integrals backwards when you're dealing with trig, because the derivative of sine is cosine. The integral of sine is negative cosine. Remember, always ask yourself, what would give me a derivative of positive sine? All right, let's keep going here. So then I got a negative cosine of 0. Now I can't leave it like this because they are trig values. So I would get docked. I wouldn't get credit if I left it like that. So negative, we do have to evaluate our trig functions. So positive. Could leave it like that, but literally, friends, negative 0 plus 1, just 1. All right, let's try the next one here. Let's see here. We got that would be tangent. So now we can find the area underneath curves of trig functions. Friends, that is cool. I'm hoping you guys find this as cool as I do. Chances are you may not be, but I'm hoping you see the beauty in it. Pi over 6. All right, we plug it in here. Tan of pi over 4. Minus tangent of pi over 6. And again, we have to simplify that. Can't leave that like that. So tan of pi over 4 is 1. Tan of pi over 6 is root 3 over 3. And we can leave our answer like that. Don't be shocked on a multiple choice portion of the test if they write your answer with a common denominator. That's possible. There we go. Okay, we're only going to do a couple more things here for the day. Like I said, today was just kind of, let's get familiar with the FTC. So, determine the area bounded under f of x equals square root of x. I'll go put that back in here in a second. It's 2. The x-axis and the y-axis from 0 to 4. So, now we don't need to graph this. You can if you want to. I'm going to graph it here so you can see it. So this is really what's going on here. So we have our axis, we went up to 1, 2, 3, 4. So they're basically saying, all right, if we treat this x-axis as a boundary and nothing comes through here, or the y-axis, if we treat the x-axis as a boundary and nothing comes through here, and we do this curve, when we separate all these things, so the curve's going to look something kind of like this a little bit. What they're really asking for is, all right, what's the area that's guaranteed to fall in between all these values? What is all this area that's in between all these things? Essentially, it's the same thing we've been doing. It's just a different way to write it. Sometimes you'll see it written kind of with that kind of notation. Well, let's try that here. So all we really are doing then on this is just taking the definite integral from 0 to 4. All right, why don't you go ahead and pause the video, see what you can do with that. All righty, let's see how you did. You know I'm going to go ahead and clean this up a little bit here. X to the 1/2 plus 2. So we're going to integrate it for the entire thing here. And then from there, we integrate it. So x to the 1/2 is going to be 2/3. X to the 3/2 plus 2x. And we're going from 0 to 4. So plug it in here. 2/3 times 4 to the 3/2 plus 2 times 4 I hear my dog playing in the background right now. Apparently she just woke up. 2/3 times 0, 3/2 plus 2 times 0. All right, here we go. So 2 is the square root of 4, that's 2. Cubed is 8 times 2/3, that's 16/3. Plus 8 minus 0 equals, oh, what's that going to be? 24 40/3. Now, I would have left my answer probably as this right here if it was on the free response, but multiple choice, we'd need to be able to simplify that out. Alrighty, so we have this fundamental theorem of calculus, and we're just going to look at one quick application of it, and then we're going to go ahead and call it a day. And that's called the average value function. So here's what it says. The average value of f of x on a to b is, and then we have a, looks like this, 1 over b minus a to b f of x dx. So let's think real quickly about what average is. So say I give you a bunch of numbers. 2, 3, 5, and 8. Say I give you a bunch of numbers and I ask you to find the average of these. And back in middle school, you guys hopefully remember that average was you add up all the numbers and then you divide by the number of numbers you have. So we add them all up, and since there were 4 of them, we divided by 4. And when we did that, we ended up with 18 over 4. So this right here, this was the value or the sum of the terms. This right here was how many terms we had. Well, this is what's kind of going on here with this. Notice I could rewrite this, that average value of a function. I could rewrite it like this: from a to b, f of x dx if I could put that b minus a underneath it. Now, if I were to have done that, what you end up getting here, friends, is essentially this up top here. That's a value or the sum, just like we did just like we had back when we were in middle school. The b minus a, that is the length or the distance between our two bounds. Okay. And so what we're doing here is really, we're just finding average, just like what it says, average value. Well, it really is the same thing as what we did before. Nothing really has changed. These two things right here, whether it was in middle school or here in calculus, it's pretty much the same exact thing. So let's end up real quickly where we actually deal with one of these. And so you can actually kind of play with it a little bit, try it a little bit, and then you'll have some of it on your homework as well. All right, final problem. Find the average value of f of x equals negative x squared plus 5x on the closed domain from 0 to 4. All right, so why don't you guys see if you can use this formula to figure out what the average value would be on this domain. Pause the video and give it a shot. All right, let's see how you guys did. So we got 1 over 4 minus 0. From 0 to 4. And we're going to find the average value, we're going to integrate that. Plus 5x. dx. So the biggest thing people forget on this is the 1 over 4 minus 0 at the beginning. So we never want to forget that. So we have 1/4. We're going to leave that constant out there. And we have negative x cubed over 3 plus 5x squared over 2. And we're going to evaluate that from 0 to 4. So 1/4. We got negative 64/3. Plug in the 4 in here. I probably should show where this is just in case. So negative 4/3 over 3. Sorry about that. Plus 5 times 4 squared over 2. Minus a negative 0 cubed over 3 plus 5 times 0 squared over 2. So we end up with 1/4 of negative 64/3 plus, let's see here, plug the 5 in there. Let's see, we have 4 squared, that'd be 16 times 5 is 80 plus 2, that'd be 40. Minus 0. So that ends up being 56 over 3. And last and certainly least here, friends, we end up with 4 goes into there 15 times, 14 times, so 14/3. So the average value of any number from 0 to 4 would be 14/3. All right, friends, well, that's going to take us down to the wire today. Tomorrow, we're going to come back and look more at definite integrals and deal with the applications of it. What applications can be used on this idea of how it applies to particle motion, or how it applies to finding the net change of a value and different things like that, as well as looking at something called the second fundamental theorem of calculus. So we're going to leave it at that today. So practice the skill, and I can't wait to see you guys tomorrow. All righty, take care.